All right, so exponential growth and decay. So you guys have actually seen this in Algebra 2 and last year and pre-calc. Usually when we talk about exponential growth and decay, it's like y equals 2 to the x power, something like that. So you'll see this graph that goes up really quick, or a graph that goes down pretty quickly. This is how it came to be that there is this graph that goes up really quick and where that formula came from. So we're going to derive exponential growth and decay formulas, basically. So there's some things in life, like population, money, radioactive elements, decay, there's like half-life, things like that you've heard of, that change. They either increase or decrease at some sort of rate proportional to the amount present. So like you put money into the bank, and then there's some sort of compound interest. And if it compounds continuously, it's something like this. There's a rate proportional to the amount present. So here's your rate, dy over dt, so in terms of time, equal to, and then some proportional amount to what you have in there. So y is what you put in there, and then k is the proportional amount. So we don't know what that is, but it's some sort of number. It's some sort of rate. So like 0.07 for 7%, whatever that is. Okay, so what you would do with this, and this is what you would do like over and over again, basically on the AP test or on the quiz or whatever. So you have this differential equation that they give you, and then we're going to do what we did a couple days ago, and we're basically doing separable variables. So we separate the t's to one side. Remember that k is a constant, so it stays on that right side. And then we're going to take the y's and bring it to the left side. And then you integrate both sides. And then 1 over y, when you take the antiderivative, is ln absolute value of y. The k is some sort of constant, so now it's kt instead of like 4 and then a 4x, it's kt. And then plus c, because there's some other constant, I don't know what that is. And then you e both sides, you have absolute value of y equals, and so we've done this part, you guys are just kind of writing it down, we're pretty used to that. And then at the end, this is some sort of constant. Here's my constant c. That's actually your initial amount, so we call it y sub 0. So usually, that y sub 0 is like, when we're talking about money, that's the principal amount. That's the amount that you put into the bank. But we can also call it y sub 0 for the initial amount of y. So this is actually the same formula as PERT, if you remember PERT. So that's the principal, and then e to the power of the rate that the bank is giving you, and then there's your time in years or months or whatever. Okay, actually in years, sorry. Okay, so this you'll see a lot, and it happens a lot, and this you'll see in like some of the other formulas that are highlighted as well. So the law of exponential change is based on that PERT formula. So you see it right here. So if it's exponential growth, r is greater, or k actually is greater than 0, and then if it's exponential decay, then your rate, which we're calling k, sorry, these are different variables, is less than 0. All right. So that's where the formula came from, but really we're going to ask you to derive that formula a couple times, like a bunch of times, okay? But if it just gives you a problem with continuously compounded interest or something like that, we can just use that formula. If they give you this, you have to derive it before we use this formula. Okay, so compound interest. This should look a little bit familiar as well. So this is what you did in Algebra 2 as well. So you put in some money, and then maybe it's compounded 4 times a year, so that n would be 4, so compounded per year. The t is how many years it's in the bank. The r is the rate, so maybe 5%, that would be 0.05. And then we use that formula, and we know how to basically use it. But we're just kind of messing with it so that we can, again, practice some of these powers and how to press things on the calculator. Continuously compounded is basically this formula, but then instead of like 4 times a year, 12 times a year, 365 times a year, so now we're saying it's continuous, so n is a really big number, like infinity. When n goes to infinity, what happens is this becomes e. That's where e comes from. That's the formula for e, basically. All right, so continuously compounded, we saw this over on the left side as well. Same kind of formula. This is our principal, and this is what you get at the end. So a couple examples of this is you have $3,000, and the bank is paying you 5% interest. How much money will you have in 10 years if A, it's compounded quarterly, B, monthly, C, continuously? You can see the difference right here. The only difference for compounded quarterly versus monthly is there's a 4 and there's a 12. There's a 4 and there's a 12. So to the power of NT, to the power of NT. And then you put that into your calculator. I'm going to guess that you can do it because you're going to have to practice anyway for your homework. And then continuously, again, is that PERT formula. So instead of memorizing like y sub 0 or a sub 0, whatever that is, I just remember PERT. Okay? And then I plug everything in. There's no n because it's continuously. So I just use my new E formula, and then you put it in, and then you can see the more it's compounded per year, the more money that you get. It seems like a little bit, but once you start putting money in, it just keeps adding, so things are good. Okay, here's the better question, all right? So that's when you get to the good stuff. So this says, how long will it take an investment to triple in value if it earns 7% interest compounded continuously? So you're going to start with your PERT formula, basically, and then it says triple, and maybe you don't know what to do, but then you realize, oh, if I put in $1, then I should get 3 at the end. So then you just put in all the information you have, 7% interest, 0.07. You're solving for t. How would you solve for t? You got to get that t down here somewhere. So you're going to natural log both sides. And then you can do the power rule. This comes in front. And you have ln, power rule. This comes in front. And then ln e is 1. So really, it's this equals ln 3. Divide by 0.07, and then when you put this into a calculator, approximately 16 years, something like that. So triple in value, 16 years. Okay, and then it gets to the really good stuff. So last example. Suppose the half-life of a carbon sample is that many years. So we have our T. Find the age of the sample in which 20% of the radioactive substance originally present has decayed. All right, so actually, they don't give you, so we have 20%, but they don't give you a rate. It says find the age. So that's like in years. All right, let's start with what we do have. So here's our PERT formula, and then half-life. So half-life, if I started with 1, how long does it take, what's our rate, for us to reduce that by 50%? So that's what we're going to solve for first. You have 5,700 years, so for t, we're replacing with 5,700. So 1/2 equals e to the 5,700 r. We're going to solve for that rate. And then ln both sides, solve for the rate. This is your rate that you had to solve for on your own. Using that rate, we plug it back in to PERT. And now we use the information that they said. Find the age of the sample in which 20% has decayed. So if 20% is gone, what's left is 80%. So if you plug in 1, you should get 0.8 at the end. You can even do like 100 and then make this 80. You're going to get the same thing. And then I'm going to plug in everything I know, including, here's our rate that we found over here. So now we're going to find the age that it is if 20% has decayed. So then now that we have this, we have all numbers except for our t. So we're going to solve for t. And then we ln both sides, and then we have to divide by this thing, which I know is really weird, but it just becomes the reciprocal. And then t equals this much, put it into a calculator, and you're going to get about 1,835 years. So it takes about almost 2,000 years for something to decay 20% if the half-life is 5,700 years. So there's how we would use something like that. Okay, the other part, I'm going to show you what you can remember, but I wouldn't really memorize this. because you can always find it every time. Some people really like memorizing formulas, so here you go. So what is the formula for half-life? So the formula for half-life is always the same thing, because when you plug in 1/2 of some value equals that value, so here's your PERT, but then here's 1/2 of our original value. So then we get this, and then we L on both sides, and then we solve for time. Time is always going to be ln 1/2 over k. So there's no reason to memorize this, but it's always going to work. Therefore, it's good to know half-life is always this. And then I added one thing in, so a lot of times it's like there's a half-life and there's a doubling rate. So what would be your doubling rate? Well, it would be ln 2 over k. So our doubling rate would be ln 2 over k, or you can say that your rate is also ln 2 over t, because if you solve for t instead of k, you would get this as well. Your homework is written right here. So here is today's homework, and then you do not have to start on the rest. But yes, on Monday, you're going to do 6.4b, and then that's it for the chapter. We have a chapter review. All right, good luck. If you have questions, leave them on Google Classroom. All right, help each other today.